So much for joining us for the third seminar of the cycle of conferences Science on the Net, organized by the specialized group on crystallography and crystal growth of the Spanish Royal Societies of Chemistry and Physics. It's my great pleasure to introduce you all to our speakers today, Dr. Petra Fromme. Dr. Fromme received her bachelor's degree from the Free University in Berlin in 1983. Her master's in biochemistry also from the Free University in 1985, and her doctorate in chemistry from the Technical University also in Berlin in 1988. She was an assistant and associate professor at the Max Bolmer Institute before joining Arizona State University as a full professor in the School of Molecular Sciences in 2022. She has published over 270 peer-reviewed publications and received international honors that include a Lambert Fellowship of the Australian Academy of Sciences, the Robin Hill Award from the International Photosynthesis Society, the Biology Award from the Academy of Science of Göttingen in Germany, the Galvin's Professorship in 2012. She has also named Regents Professor in 2015 and recently honored with the prestigious Amundsen Award by the Protein Society, which is given in recognition of significant technological achievements and or methodological advancements in protein research. From 2010 to 2014, Dr. Fromme was the director of the Center for Membrane Proteins in Infectious Diseases, which received about $8 million for investigating the structures of viral, bacterial, and human membrane proteins involved in pathogenesis. Since 2014, she's the director of the Center for Applied Structural Discovery. Dr. Fromme's research interests are in studying the structure-to-function relationship of membrane proteins involved in bioenergy conversion and infectious diseases. And to finish, she was an integral part of a team of ASU researchers and international colleagues that developed the technique of serial femtosecond nanocrystallography for analyzing proteins using the high-intensity X-ray Free Electron Lasers. And with that, I'm gonna ask Petra to share. Oh, she did already. So, and before I forget, I'm gonna ask the audience to type any questions you guys may have in the chat or the Q&A window. So, and then after the talk, both Armando and I will go through the questions. So with that, Petra, please take it away.
Okay, thank you very much. Thank you very much for the really nice invitation to give us a seminar or webinar at the GEC Institute. And I'm really excited about giving you the talk, but I would be even more excited if I could come in person, because it is such a pleasure to be at different institutes, learn what you're doing. And so I hope that when COVID is over, that I can come in person. So today I want to tell you about molecular movies of biomolecules in action with X-ray Free Electron Lasers. And not all of you might have been able to come to Arizona. Before I came, I actually thought that would be a plain desert looking like Sahara with some big cactus on it. But in reality, it's the really most beautiful landscape I've ever seen. And this was together with the science which drew me to come to Arizona. So I'm leading as Jose, thank you very much for the really nice introduction. As Jose told you already, I'm leading as a director of the Center for Applied Structural Discovery at the Biodesign Institute. And we want to develop revolutionary new techniques that reveal the structure and dynamics of biomolecules towards visionary new discoveries in medicine and energy conversion. So we have two major applications: energy, which I will tell you at the end a little bit about it, and then medicinal relevant projects. So the X-ray projects are large collaboration. I'm sure that I have not all collaborators on here, which involves our team at ASU, where also Jose was a team of. Then we have, when he was at ASU, then we have a big collaboration with the team of Henry Chapman and his team at CFL at DESY in Hamburg. Then we have now collaboration with Jose at CSIC in Spain. And then we have also, I have also a small team at DESY working essentially on developing of compact free electron lasers, which I will also tell you a little bit about at the end. And then we have a big collaboration with Marius Schmidt, Abbas, and Peter Schwander at UWM, with Sebastian Boutier at SLAC, Lawrence Livermore National Lab, Hauptmann-Wuttmann Institute in Buffalo, and also with the European X-ray in Hamburg. So now, what are the members of my center? So the Center for Applied Structural Discovery has 16 faculty members, and each of them has 4 or 5 students or more. So we have in total, we are close to 90 people in the Center for Applied Structural Discovery, and we come from very different backgrounds. So you have members of the team like John Spence, who together with me have practically pioneered free electron laser work together with Uwe Weierstahl. And Alexandra Ross is also an essential part of the team because she works on microfluidics and all these sample injections. So you have people working on the technology development combined with people working on the applications. From Brenda working with virology and single particle X-ray imaging, Deborah working on immunology, by Leo on G-protein coupled receptors. These are more the medicinal relevant, as a faculty working on the medicinal relevant things, together with people more on the photosynthesis side with Gary Moore, Raimund, and Yuval. And we combine practically the exciting biological questions that we want to answer with these technology developments. And we are not only involved in using free electron lasers, we are also involved in building free electron lasers here with Bill Graves' work developing compact X-ray sources. And then we have also Rick Hirian and Scott Cyrus, who will develop a new SFX method and also on attosecond X-ray spectroscopy. And we are not only focusing on X-ray spectroscopy, we have also essentially a strong group with Abhishek on computational studies, and we have also cryo-EM and microelectron diffraction, which I will not talk today about, but these are also really exciting projects which we work on. So we try to establish a huge method spectrum of getting structure and dynamics of biomolecules in the center. So where do we actually came from historically? We wanted to get new avenues for structure determination of large complexes. So for example, it took us 13 years from the first small crystals of photosystem 1 to get in 1988 to get the near atomic structure in 2001. And this was still kind of stone age of membrane protein crystallization. So it's still one of the most largest and most complex membrane proteins ever crystallized. And we want to develop new techniques to determine atomic resolution structures of large molecules with nanocrystals. And when we tried this more or less shortly after I came to ASU, John Spence approached me and said, do we have any use for X-ray free electron lasers? And do we want to develop some new techniques together? Then we submitted from 2003 to 2009, when we did the first experiment at an X-ray, submitted more than 10 grants with all the ideas of delivering the crystals in a jet and hitting them with X-rays and being able to measure structures at room temperature and eventually molecular movies. And they were all rejected because the referee said, this is impossible. And so I want to tell you a little bit about why they think it's impossible. So here you see actually the picture of LCLS. That was the first X-ray free electron laser in the world developed. And X-cells make X-ray pulses that are 10 to the order of 12 stronger than the strongest synchrotron. And they are so short that Neutze and Heido have proposed that they would outrun the X-ray damage. So at the bottom, you see a picture of a molecule exploding in an X-ray beam from this paper from Neutze and Heido in 2000. And they simulated that it would take about 10 femtoseconds for the molecule to explode. So the idea was that when you would be faster than this 10 femtoseconds, then you would get a picture of the molecule before it is destroyed. And 10 femtosecond is extremely short, 10 to the minus 15 seconds. That means the time difference between a femtosecond and a second is the same as between a second and 32 million years. So that was great, but the referees didn't believe that. They said, A, they don't believe that you get diffraction of a biomolecular crystal before it is destroyed. B, they said, even if you get diffraction before destruction, you would be never able to evaluate the data, because the argument was as follows. The X-ray pulses are 10 to the order of 12 stronger than the strongest synchrotron. That means the flux per second. But the pulse duration is only a few femtoseconds. And so you have a 10 to the order of 12 stronger pulse, but you have a 10 to the order of 15 less time. So that means their calculation was that you would have 1,000 times less flux in a femtosecond X-ray pulse compared to, let's say, a second exposure at the synchrotron. And then we propose to use only nanocrystals, which contain only a few hundred or 1,000 unit cells instead of a big crystal with millions of unit or trillions of unit cells. So they said even if it diffracts, you would never detect this because a signal would be too weak. And then the last argument was that all diffraction spots would be stills because you jet the crystals through the beam and you get practically only a still image instead of a rotation image. And so you would never be able to determine structure factors. So all our grants were rejected. And this was the status when we did the first experiment in 2009. And this were the results. And they were truly spectacular. So we used actually photosystem 1. At this time, the largest and most complex membrane protein ever crystallized as the first model system. And even my colleagues said, you are nuts. You know, Schlichting said to me, how would you ever consider to take photosystem? Nobody believes that the method will work. And you want to take the largest, most complex membrane protein so far crystallized as the first model system? That's a really bad idea. We should use lysozyme, and then when the lysozyme diffract, maybe in 10 years, we can try photosystem. But my argument was that when we have only low resolution reflections, then we would see something with photosystem 2, because photosystem 2 is really large. So we would even at low resolution be able to see a structure. And also the reflections, it would have more reflections on the beam. So anyway, we had the hot discussion during the beam time already when we prepared for the experiment. And then Henry Chapman, who was the lead, said, well, let's be adventurous. Let's take photosystem 1 first. And when it doesn't diffract, we can always put in lysozyme. So everything is history. And in retrospective, we will never be able to index any of the patterns from lysozyme because the beam was only 8 angstrom. So we were limited to this medium resolution range. And we had too few reflections of lysozyme on the detector to be able to index it. So if we would have started with lysozyme, there would have probably no SFX, because people would have said, when you cannot even solve the structure of lysozyme, what is this method good for? So it was a good choice to use photosystem. And you see here the 8 angstrom structure solved here. And the really cool thing is when you see here the jet, so we deliver the crystals in a jet, you see this glow. This glow comes actually from the interaction with the X-rays. And we have calculated that the intensity of the beam would be so high that you would form a plasma. And this is what you actually see glowing. And then here on the front detector, we saw very strong reflections. And you remember this, my talk about that you would not be able to see anything. We saw diffraction to the edge of the detector, and we have even overloaded with these little nanocrystals being less size than the size of the light, saturated the detector. And we were also able to show that we really get diffraction from nanocrystals, because Zayas has proposed in 1952 that if you would ever get diffraction of a crystal which has a countable number of unit cells, you would see fringes between the peaks. And these fringes, you would just count them and you see how many unit cells you have. And when you just evaluate one of these so-called shape transforms, you get the size and the shape of the crystal. We know that this crystal was 620 nanometer, and you even see the hexagonal shape on the evaluation of the shape transform. And therefore, we know that we evaluated multiple of these shape transform patterns, and therefore we know that the smallest crystal we diffracted was only about 120 nanometer. And that means it had 3 by 3 by 6 unit cells only. So that was really exciting. And since then we had more than 25 publications in Nature and Science and journals. Actually, we are close to more than 30 now. And I just wanted to highlight some of them, including this one on the structure of Cat-B from crystals grown in vivo. I told you that we can use now crystals which are smaller than the wavelengths of the visible light for structure determination. And so our colleagues in Lübeck, Lars Redeke, had tried to get the structure of a protein called Cat-B, which is actually causing sleeping sickness. Not causing sleeping sickness, but degrade your red blood cells when you're infected with bitten by a mosquito and get sleeping sickness. And they detected that there are crystals forming inside the living cell. Here you see a crystal of Cat-B. And we were able to isolate these crystals and jet them to the beam and get the structure of Cat-B together with a peptide which inhibits the function of the protein in the mosquito, because the mosquito don't want the protease to degrade all his proteins. So it's the natural N-terminal peptide is inhibiting it. And when it gets into your red blood cells, it gets cleaved. And you see how well now the structure is defined, including seeing all the glycochains, which essentially are involved in this peptide. And this paper was actually highlighted as one of the breakthroughs of the year in science in 2012. It was not the breakthrough of the year because it was a Higgs boson. Nobody can beat the Higgs boson, but we were one of the 9 front runners. So in the meantime, we have used novel techniques developed actually by Rosé and Martin Garcia and also Nirupa Nagatna to express proteins in living insect cells. And we labeled the protein with eGFP so we can see the crystals. And you see now with improved expression conditions you can for this protein microRNAs, we could get crystals forming in nearly every cell. And we could also embed the living cells in agarose for direct delivery to an X-ray beam. So we were wondering actually when we express the protein, how the crystal formation works, because when you, after 1 day of induction, you see the complete cell glowing. So the protein is not crystalline yet and are distributed in the cytosol. And only after about 2 to 3 days, then these crystals form. But as soon as the crystal is forming, the cytosol is completely dark, while we are still seeing the crystals growing. So how can a crystal grow when the protein is not in the cytosol anymore? So we looked actually at electron microscopic pictures of the crystals, a negative stain. And you see here the nice crystal lattice, and you see at the surface, these crystal surface that are very likely ribosomes, polysomes, attaching to the surface of the crystal and thereby essentially helping it grow. And we got just last week the announcement that we got essentially seed grant from the Alzheimer Foundation, where we want to investigate with similar methods the formation of aggregates of the tau protein in the brain. And one of the goals is to use methods like cryofib to determine if also in the brain the growing aggregates of tau might be formed by ribosomes docking on the, in this case, not crystals, but docking on the aggregates. So I'm very excited that this is, with these results on the crystals, we might be able to make an impact on Alzheimer's disease and the understanding how these aggregates form. This paper here was published just last year in Acta Christ F. So then the title of my talk is Molecular Movies, and we made several experiments in the past 5-6 years on getting time-reserved information on proteins, because proteins are dynamics, but most of the structures which have been determined today are static structures of a molecule. And so when you look at examples for X-ray studies, which I want to elaborate a little bit on, then one of the exciting discoveries was on the gene regulation. Then we also looked at enzymatics reaction and also ultra-fast light-driven reactions. So let's look a little bit at the gene regulation. So that's a paper which we published together with Dr. Wang from the National Cancer Institute, which looked at riboswitches. So riboswitches regulate gene expression by switching between these distinct RNA structures in response to binding of small metabolites. And they make huge conformational changes, which you see here in the bottom. So actually, Dr. Wang posted a video of synchronous swimmers simulating this conformational change. And so you can ask yourself, how can you actually accommodate such a large conformational change in the crystals? Because that was one of the critiques which referees always had for our grants, that they said, oh, this is all great, this time without studies, but how could you actually look at large conformational changes? And the trick here is that the crystals actually change. So the molecule makes a large conformational change, which leads even to a complete repacking of the molecules in the unit cell. So the molecules change their conformation and the crystal survives that. And the referees could first not really believe it, that you could have a rotation of the molecule by 30 degrees in the unit cell and still maintain the crystallinity. And this only works for the really small crystals, because the team of Dr. Wang has tried to induce the adenine, which induces this conformational change in the crystals, in big crystals, and they always cracked and didn't diffract anymore. And then recently he gave a talk at ASU remotely, and he showed a really cool picture where they use AFM to look what happens in the crystal in this conformational change. So they let diffuse adenosine in from one side, and then you see that the molecules in the crystals change their conformation layer by layer, like a domino effect. When you have the dominoes all in a row and you touch one, they fall all down. And this is actually happening in the crystal. And this also shows that you can mix and inject. This was an easy experiment. You have practically a substrate in one reservoir. You have the crystals in the other one, and then you just use a T-junction to mix it. We had mixing times of multiple seconds. And but the really cool thing about this result is that it shows that you can even detect really large conformational changes and get a molecular movie of this dancing aptamer from serial femtosecond crystallography. Then another really important topic is visualizing enzymatic reactions. And this is here an example of visualizing enzymatic reactions of a protein called BLAC, which cleaves antibiotics and thereby contributes to this multi-drug resistance, which is currently a really big problem, with time-reserved crystallography. And now the injection systems have dramatically improved from the first kind of quick and dirty attempt. So the team of Louis Pollack developed these really awesome injection nozzles where you can have in the middle the crystals and substrates on the side, and then you have a mixing zone where the two mix. And then the distance between the mixing and the ejection where you hit it with the X-rays is then your mixing time. And she has even developed these systems retractable, so you can with one nozzle change the time delay between the mixing and the hitting it with the X-rays. And with that, Marius Schmidt and his team, with our collaboration with us, were able to really see for the first time practically an enzymatic reaction in action. So you see at 30 milliseconds, the substrate approaches, and then you have actually at 100 milliseconds forming a covalent bond, which is then extended and cleaved again in the steady state. That means we were able to track the transition state, in this case at about 100 milliseconds, where a bond is actually formed between the serine 70 and the substrate. And this was very exciting, very exciting. So then I want to come to photosynthesis. Why we are interested in photosynthesis? Photosynthesis transformed our planet about 2.5 billion years ago from something which looked more like Mars into the nice green planet we see today. And there are two large membrane proteins complexes involved in that, photosystem 1 and photosystem 2. And photosystem 2 will be the major focus which I talked today about it, even if we have also exciting new results on photosystem 1. So the goal is to develop time-reserved SFX with laser excitation to determine the mechanism of water splitting, which is a kind of holy grail of photosynthesis, because all the oxygen that you breathe has been evolved by this process. And if one would understand how nature with earth abundant metals and sunlight could split two water molecules into oxygen for electrons and for protons, then one can build artificial systems which are as efficient as nature, but as stable as man-made system, because photosystem 2 lives in a plant in bright light, sunlight only half an hour. So half of the energy which the plant captures is for replacing PS2. And the problem is not the water splitting, the problem is the light reactions. Because chlorophylls, what is green in nature, contain magnesium in the center. And magnesium is not a transition metal in a porphyrin ring. So that means the damage which happens to photosystem 2 is actually to the light capturing and charge separation part, not to the water splitting. And so artificial system could fix that and using much more stable pigments for light capturing. But first we have to know how the water splitting works. And so we did time-resolved experiments where we now have the crystals jetted, and then we can expose them on the fly to 1, 2, or 3 laser flashes to cycle photosystem 2 through the system. Let's see if my video works. And this is actually from the very first beam time, still at AMO at 8 angstrom, where we collected data on PS2. And this is kind of gives you an impression how it looks like, because sometimes you hit a crystal and sometimes you don't hit a crystal. But if you hit a crystal, the diffraction is really strong. And at LCLS, the pulses come with 120 pulses per second. So you measure 120 patterns, which could be either hits or non-hits, and to get essentially a structure of the molecule from it. But you have to determine structure from about 20,000 images at least to essentially get good structure factors. You remember that the referees were doubting if one get any structure factors. So you have to measure each structure factor at least 100, better 300 or 1,000 times to get correct intensity of the reflections. So this is then the experiment, more a schematic scheme. So we flow the crystals through the X-ray beam. We illuminate them in a wide range, so in the nozzle and covering the nozzle, the jet, and the interaction region. And then we set it so that every second X-ray pulse triggers the laser, the visible laser. So this laser pulse triggers the light, this not, this triggers, this not. And when you do this, you get one light pulse, one dark pulse, one light pulse, and one dark pulse. So it means in 1 second, 60 lights and 60 darks. So this was now the sphere of reflections from this first photosystem 2 time-resolved data set, where we measured in total the about 3,500 reflections at the highest resolution, which was 5.26 to 5.8. So in the outer region here, we measured them for the we measured for the dark set data set more than 2 million reflections, and for the light data set about 1 million. So it means our multiplicity, that's not the redundancy, multiplicity, because you have to measure each reflection multiple times because each one is only an ultra thin slice through the Ewald sphere. We measured them more than 600 times for the light data set and more than 300 for the dark data set, and more 300 times for the light data set. So then we got the first structure, and it was limited to 5 angstrom, but the dark structure kind of matched the high resolution structure which the Japanese group has solved a little bit before. And here you see now the large conformational changes that happens in the light. And because it was low resolution, you have to take what we saw with a tablespoon of salt. But higher resolution structures solved in the meantime actually showed that the main hypothesis which we brought forward is actually true. Because we said that in this double excited state, this manganese would move forward. And this would allow a new water molecule to come and make an oxygen-oxygen bond with this oxygen here. And this was from a simulation here from ISO, but all which our structural investigation would support. And in the meantime, the Japanese have actually seen that oxygen coming into the binding site and making these bonds. So it was very exciting. But what is still missing is a high resolution structure from the transient state where the oxygen-oxygen bond is formed. But because it is transient, you can, it is difficult to reach, and you would need 3 laser excitations for that. So this is what we have published in 2014, and this is what we are working on to get the structure of the transient state where oxygen is evolved. And also we want to combine the results, the experiments with X-ray diffraction, with X-ray spectroscopy, So we would see the oxidation changes of the manganese at the same time when we collect the X-ray. So we should see that the manganese cluster goes from the most oxidized to the most reduced state back, how oxygen is bound and how the first substrate water is bound in this transition. And we have experiments upcoming in October where we will be able to combine X-ray diffraction with X-ray spectroscopy to investigate this process. So keep tuned on the transition state and the real mechanism of water splitting. So then I want to just tell you now a little bit about serial crystallography of medical relevant membrane proteins. And one of the techniques developed actually by Leo and Vadim Sharetsov is serial femtosecond crystallography of membrane proteins in lipidic phases. Many membrane proteins, including these G protein coupled receptors, which are important for human health, are very unstable in detergents. So you have to embed them in a membrane environment to be able to maintain their stability and to crystallize them. And this method has been now used for many different proteins to get structures, static structures at the moment. So we have here, for example, structure from the angiotensin receptor, which was solved with the drug bound, which you know then all the details about it. And because the crystals are very radiation sensitive, the structures, when you compare structures determined from GPCRs from this X-rays sources at synchrotrons and X-fields, the X-fields always show you better details. So now more than half of the new GPCR structures are come from X-field studies. And one of the really tough nut to crack was actually this mucin receptor here, which actually is involved in cancer and also in embryonal development. And they have actually tried to crystallize it for a long time with a molecule called cyclopamine, because sheep feeding from corn lilies, which contain this toxin, gave birth to sheep which had only one eye in the middle and were heavily deformed. So they looked like a cyclope, and therefore the compound was called cyclopamine. And variants of cyclopamine are now in clinical trials for anti-cancer. You should obviously not give it to pregnant women, but it seemed to be like a very potent drug. But they could not get any structure of this receptor with cyclopamine until we did SFX experiments on it. And you see here now nicely the drug bound in the binding site. So this was very exciting results that we, and this also so far the only structure with the GPCR and the drug where the drug is not bind in the membrane region, but in the extracellular region, thereby changing all the conformational changes from these loops, which explains its strong inhibitory effect. So when you can now solve structures and hopefully in the future also dynamic structures from these medical relevant drug targets, then you can use the target structure with the library to do virtual screening, compare this to binding assays, which then informs your modeling again. And so you can bring a drug in much faster time to preclinical trials. And also you can make one which binds much stronger. So while Leo has with this design been able in 2 months to change the binding affinity of the initial drug of about a micromolar to 5 nanomolar with this kind of design. And ideally you want to know not only the static structure, you want to have a transition state. And we got a project funded now from National Institute of Health, where we will try to get a molecular movie of the GPCRs. And this is not easy because I told you they're embedded in this viscous media. So you cannot use mix and inject, and they're also not light driven. So our strategy is to use a caged drug, which is synthesized by Diana Montero from University of Buffalo, which you can release with a laser flash. So the idea is you have practically the drug combined with a big fluorophore, so it cannot bind. And then you would embed it into the LCP, and just with a laser flash, you would release the substrate, which then can bind. So we want to make the GPCRs light driven. But we're just in the beginning of the project. So we have just the first compound synthesized, which binds to the beta adrenergic receptor. And hopefully soon will do the first time observed experiments. We got beam time in November for this project. So we hope that by then we have it established and can try to make essentially the first little molecular movie of a GPCR. So then I want to, at the end of the bio part, tell you more about time-observed studies on a project on the SARS-CoV-2 virus, which I know for easier explanations, just call it COVID virus, okay? Officially, it's called SARS-CoV-2. And we had, this protein is called NANDO-U. And I presented this for the first time at the Bio-X-ray conference in 2021, but we have not published these results yet. So why we are interested in NANDO-U? So normally when you have look at COVID, which now is in everybody's interest, most interest on COVID actually focuses on the spike protein. So all the vaccines are targeted to the spike protein because it docks to the cell and thereby essentially allows the virus to enter the cell. But it doesn't explain really, when you study the S protein, why is COVID a pandemic in contrast to SARS and MERS? And this is why I will tell you a little bit more about. So one of the important things have to know for the story is when you look at the RNA of the coronavirus, all coronaviruses, and from that including SARS-CoV-2, the RNA comes in the virus ready to use. So it means it looks like an eukaryotic, already fully processed messenger RNA. So it contains a cap and a long poly A tail, which are both needed for the ribosomes to recognize the RNA. So what happens when you now infect, when the cell gets infected with COVID? First, it enters the cell, then uncoating happens, and then this messenger RNA, the RNA is directly ready to use to make essentially a big pre-protein with open reading frame 1A and 1B, which contains, for example, the replicase, the protease, and also NANDO-U. And then a negative strand is made, which you need A for replication of RNA, making large amounts of positively stranded RNA, but also then serving as a template for making the messenger RNAs for the structural proteins. So the non-structural proteins, which are the more interesting one because they're the enzymes, are made right away from the messenger RNA, and then the spike protein and the other ones are made from the negative strand. And when you have now a negative strand RNA, it has a poly-U header. So this poly-A tail becomes a poly-U header. And poly-U headers never exist in the human cell. So they are single for viral infection with an RNA virus. So over millions of years of evolution, our immune system have been adapted to detect that poly-U header and practically introduce a virus alert. And so the difference between COVID and the other coronavirus diseases is that we don't get fever right away when we get infected by it, and thereby can spread the virus while we show no symptoms. And that's the reason why we have the pandemic. And the protein we are looking at is at the core of that, because that NANDO-U was long time a mystery. It is present in all of these highly virulent coronavirus strains, and it is specific to coronaviruses. But it's not involved in the replication or in transcription. So people were wondering what it is doing, and then just last year it was discovered that it actually cleaves this poly-U tail or header, and thereby hides the virus from the immune system. So COVID, so the NANDO-U protein is practically one of the reasons why we have this COVID pandemic. Because the hiding of the immune system leads to the fact that you don't get fever right away, you don't show symptoms, and you spread the virus really bad. So NANDO-U cleaves that poly-U tail off. And we want to get the structure of this protein and hopefully also molecular movie of its action. So then we made really nice crystals, and Jose was actually establishing the first crystallization conditions when he was still at ASU for it. And then we tested the cleavage in the crystal. And you see that the protein is highly active in cleavage, both in solution and in the crystal. And in contrast to this publication here, where they said that they need manganese for being able to cleave. So here with plus manganese, no cleavage without manganese. We actually see cleavage even in the absence of manganese. So just with sodium chloride. And so this means that the protein is in the crystals in a very active conformation, where it is actually cleaving the RNA faster than in solution. So that is really exciting, especially when you want to do chemosynthesis studies. And so this is the first experiments we did in August 2020. So we have in principle anti-settler device, and we have a mixer. We have two different types of mixers. And then we wanted to do this time-reserved experiment. So we established two different sample delivery systems, one 3D printed and one with this mesh system, and delivered the crystals to the X-ray beam. Here's the X-ray beam, and then detected the images on the detector. And we were the first users being able to come on campus, and X-ray experiments in time of COVID were really challenging. So we actually, Rebecca and I drove with all the equipment and the viewers and the samples to LCLS, which was a 2-day drive. And then we had to be all masked up and work with social distancing and so on. So you see here Rebecca, and then the sample delivery team with Deandra and Mukul, and then also Denuwan, who worked on the functional assays, joined us for the second COVID same time. So it was a big effort getting permissions to travel from ASU. Even you have to get permissions from the dean, the provost, and the vice president of ASU to be able to travel, and the president and the director of SLAC. So it was quite an effort. But it paid off. So you see here now the first crystallization condition, which actually Rosé had developed. So with little kind of needle-shaped crystals. And this is a needle. These are the shards from Rosé. So they're very small, only 2 by 2, and they're crystallized here in conditions with sodium citrate and PEG. And the other one is without any precipitant, just at low ionic strength concentrating the crystals. And even if these crystals made just by concentrating looks much nicer, they don't diffract so well. They diffract only to 4.5 to 6 angstrom, whereas these nice crystals here grown in citrate diffracted to 2.5 to 3.5 angstrom. So we were super excited. We collected a full data set, mixed it with substrate. And I just want to show you here. Let's see if it works. Yeah, this is the data set we collected. On the left side, you see the accumulated images, already seeing kind of virtual powder rings. And we reached hit rates of up to 20%, which was really, really great with the mesh injector. So 20 means every 20 is every 5th pulse would have an X-ray diffraction pattern. So then we get really nice data statistics to 2.6 angstrom for this data set, and we have deposited this already in the PDB. But when we looked at the binding site, unfortunately, it doesn't contain our RNA, which we mixed it with. It contains citrate. And so that was a little bit frustrating. And because and we wondered, how can citrate be in the binding site and the crystals cleave so fast? But we think that the RNA binds really strongly, gets cleaved, and then we have 100 millimolar citrate, and citrate binds back. So the state where the substrate is bound is only very transient. The enzyme is very active, and as soon as the binding site is empty, citrate rebinds. So then we tried to wash the crystals, and this was actually quite exciting because we were able, in the washed crystals, to see in one binding site there is still blob from citrate, but in the second binding site, in the A binding site, you see water molecules in there. And this is very exciting for future experiments because we can now use new crystallization conditions without citrate or use citrate crystals which are washed to look at a molecular movie. And when you look at the binding sites, you see that they're actually different. So one of them is actually the one which can exchange, and this is actually the more hidden one. So this is the one which can exchange, and this is the one which cannot exchange. So the two binding sites in NendoU are not equal. And we got more beam time awarded in 4 weeks from now. Just learned last week about this. So we have to hurry up to make more NendoU. And we have also now made mutants of the protein, which actually have different cleavage efficiencies. And we hope that at least one of the mutants that can bind substrate but not cleave it, we might be able to express in large amounts in the next 2 weeks. And also look at that, because that gives us the best chance to see it in the binding site. So keep tuned for the time resolved studies on NanoU, because it may solve the structure of it in the transient state. And then when we have a transient state of NanoU, we might be able to find inhibitors which blocks that. And this would then hinder the virus to hide from the immune system. Anybody who would get infected would immediately show symptoms, and also very likely would not get severe COVID, because the immune system would right away attack the virus. So it could be a very important cure for the pandemic. So we really hope that NanoU will help us with that. And because it is conserved in all coronaviruses, when the next bad bug comes from the bats, which are the source for the coronaviruses, there's a potential inhibitor against NanoU from SARS, from SARS-CoV-2, would actually also maybe inhibit the enzymes from other emerging structures, for other emerging viruses, because there can come a virus in 3 years, which might be as infectious as COVID, but as deadly as MERS or SARS. And this would be really bad. So we have better prepared for that by an inhibitor, which could rescue us. So that's what we are trying to do with this time of studies. And it could have a big impact on drug development. So, so then in principle, let's skip this part of the project. Come on. Oops. So now I want to, oops, too far. So now I just showed you all these really cool results on free electron laser work, which we have done. But one of the challenges is to get beam time, because beam time is very difficult to get. And so often you prepare a year for essentially an experiment. And, and then you have just your 6 hours or 2 days of glorious shots when you're lucky at the extra. So the idea was then born by actually first by Franz Kärntner and his team when he was still in MIT. They worked actually on the development of a compact version of an X-ray for 20 years, but they never get really much funding for it. So then Franz Kärntner got to Hamburg. And then in 2013, he approached me and Henry Shepman and Ralf Assmann and said, what about we are trying to get money from the European Research Council to build the world's first compact free electron laser. And the idea is that you would replace this on magnetic ondulators in the big X-fields by an inverse Compton scattering. One way you hit the electrons flying with the speed of light heads on with the ultra-fast visible laser beam. And this would displace the electron, and thereby it would emit these short X-ray pulses. And then Franz's idea was also to have not randomly distributed electrons in the first place, but use also terahertz lasers to emit the electrons already in a bunched way. So they would practically, when they hit the laser beam, would already be fully coherent. So the idea was it would outrun any X-ray damage, shrink an X-ray from 1 kilometer to a meter, and reduce the cost from 1 billion to 20 million. So that sounds too good to be true, but this is what we tried to do. And we got 14 million euro from the European Research Council in a synergy grant, which runs actually until this summer in a no-cost extension to build the system. And my part of the project was to give the motivation. This is actually photo system and molecular movies, and to build spectroscopy. Actually 2D spectroscopy combined with X-ray spectroscopy. So you would get an atomic level 3D structure, you would get the electronic structure and the oxidation states at the same time. So that was the idea, and this is what we are working on. But then Hamburg tried to attract me. They made me a really nice offer. And then ASU was also excited about it. And they offered me to have a 50-50% appointment. And nearly everything was already ready until 3 days before we were supposed to sign this contract. When then Hamburg said, no, 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 no. German professor has to be 100% in Germany. So Petra Fromme, when she comes to Hamburg, has to be, Hamburg must be her only journey home, her only academic appointment, as a first affiliation on all her papers. And then we allow her graciously to spend up to 15% of her free time in Arizona, but not as a regular professor, only as an adjunct professor. Then ASU said, no, this is no option. When you sign that contract, you're out of here in 3 weeks, but we want to make you a counter offer. What do you want? And then I teamed up with the Department of Physics and the Department of Engineering and my School of Molecular Sciences. And we made this proposal to start this Center for Applied Structural Discovery and build a compact X-FEL at ASU, which is pretty crazy because we had absolutely zero accelerator experience, but we had this big vision. And so we recruited Bill Graves, which had worked with Franz Kärntner at MIT. So he was part of the same team for 20 years of building a compact X, where we attracted him to come to Arizona to work with us on building a compact X. And in the offer letter from ASU, they also said that the accelerators, that they gave us $7 million for starting of the project. And they said we will need a new building for accommodating this X-ray free electron lasers. So we are at the moment working on building the first compact X-ray in the US. The first state is not lasing yet. It's the compact X-ray light source. And the second state will be the full-blown compact X-ray. So custom design for bio application, combined also with spectroscopy. And we might at the end with the CX-ray reach sub-femtosecond pulse duration and overcome any damage limits. So there are now 2 compact free electron lasers under development, and I'm involved in both, one in Hamburg and one in ASU. And at ASU, we were actually able to convince our president to build space not only for 1 free electron laser, to build space for 2. Because our idea was that when you develop the first one and it's working, you want to do experiments. But when you want to upgrade it now, for example, to a lasing version, then it would be out of work for like 2 or 3 years. And so we've always wanted to have 1 working one and then 1 which is newly developed. And so we built then X-ray labs for 2. There's 2 walls where the accelerator will be located, 2 hutches side by side, 2 laser labs where this ultra high powered laser is located, RF rooms where the Klystron power supplies are, and then also bio support labs. And this is here the design now at ASU with the Klystron power supplies, the beamline, the high powered laser. The German company Trumpf took 2 years to build this laser. This is 80 trillion times stronger than your laser pointer. So it is the first of these high-powered lasers in the world. And then here somewhere will be the interaction region where the light from the laser will hit the electron beam flying with the speed of light. And then here comes our beamline in the hutch. And so here are some pictures of the different elements we have. The Klystron power supplies, the laser system that is not fully installed. And this is a new building. We built it in record time of 1.5 years, including all the specialized labs in the basement. And in Hamburg, at the same time, Daisy was just able to clean an old part of the old accelerator tunnel of Doris and paint the floor green, because green was standing for photosynthesis. But they were not really putting much effort into this, into the infrastructure for this project. So Hamburg has painted the floor green in the same time when we built this building. And this is here the vault where the accelerator goes. And this was in the fall 2019. And this is in winter last year when we already started to build the system up. And this is how it looks now. So you saw this kind of drawings. Here is a gun. Here's the accelerator. And here is essentially then the part where the beam is focused. And this is very exciting results just from February 27, where we got the first electrons. So that's our first electron beam, yay. And we are working now on the first X-rays. And one of the challenges is that the laser has to be fully commissioned, and this has to be done by the company building it, but they cannot come to the US. And so we have now bought these virtual headsets where then our laser scientists will work remotely with the company in Hamburg, in Munich, to install this high-powered laser system. And so we hope that in the fall we have the first X-rays and can start with the first experiment. And also access made progress. We will have not within the funding project X-rays, but I will go in July to Hamburg and we will commission already all of the spectroscopy. And then we hope that Hamburg will be very likely having X-rays in the fall, in the end of the fall or next year. So we first thought, because Hamburg had 2 years head start from us in Arizona, that we would be the first in the US, but we might actually at Arizona the first in the world, followed shortly by essentially the project in Hamburg. So this is just the difference between the random electron spacing and the coherent X-rays. And at ASU, we had got now funding for the design of the lasing version. And we have submitted an RI2 for 80 million to build the lasing version. So cross your fingers that we will select it from the pre-proposal to submit a full proposal. We hope to hear in June from them if we are selected. And so when it all works as planned, the final version, the lasing version, so the second one, will have a spectra which is even better than the Sarser spectra of the big X-fields, and seeding of the big X-fields with the small one could actually improve the performance of the big one by a factor of 100. And then we might be in business to get single molecule diffraction from an X-field. But this is music for the future, maybe in 10 years. And I want to thank now Mayo, Mayo Clinic Structural Biology Alliance, National Institute of Health, Center for Membrane Proteins and Infectious Diseases. And our biggest funding source is actually NSF, the Science and Technology Center, which funds all the technology developments. And we have also a project with the National Cancer Institute from the Center for Membrane Proteins and the Center for Membrane Protein Drug Discovery. And here are the members of the team. I want to just specifically mention Jose, who was very instrumental in several of the projects I showed you, including the initiating with me the NanoU project, who is now at your institute and continues to collaborate with us on the project. And he actually sent samples for beam time on mix and eject, which will happen next week. Yeah, it's a free electron laser. And I thank you for your attention.
Okay, Petra, thank you so much for this great and exciting talk. Now it's time for questions. There are 2 questions in the chat. First question from Xavi Carpena. He's asking, can you give us some more details about the mixing zone of the injector in your BLASI project?
So the mixing zone is actually a microfluidic mixing zone. So you have in the middle the crystals, and on the side, practically the substrate is mixed in. The fastest time resolution, the shorter, the smaller the capillaries and the smaller the mixing chamber, the faster time resolution you get. So with a really small mixing chamber of about 25 microns, you can reach actually below 10 millisecond resolution. But then you are limited with the size of the crystals, and you also have to run this really fast to be able to do the mixing. So we are actually using a slightly bigger mixing chamber, which is about 100 microns. So we were able to get down to about 20 milliseconds in time resolution. So the mixing chamber is size is directly correlated to the time resolution you can get, but you can use only really, really many crystals, because the mixing chamber is a little tricky thing concerning clogging. So the first version was the crystals came from the side. We never got a crystal to the beam because it was always clogging. Crystals should flow just straight, and mixing should come from the side. Okay.
Thank you. Second question from Ciencia Giannini. She asks, what about radiation damage issues for all these bio-X-ray related problems?
Okay, so the original simulation from Richard Neutze showed that you would need about 10 femtosecond to outrun the damage. Most of the X-ray experiments which I actually showed are in the range between 30 and 40 femtoseconds. So you could ask yourself how much damage is involved. And Henry Chapman has actually proposed that, because as soon as a crystal is exploded in this Coulomb explosion, so all the atoms are positively charged because you have ripped them off of the inner electron. That means the Coulomb explosion is either the crystal is there or more or less it is completely exploded. So when you have already crystals which are exploded, they will increase the background. And this is what we have seen. So we measure data at 15 femtosecond and at 40 femtosecond, and you have less than half of the intensity when you go with 15 femtosecond, but you still have 80% of the diffraction. And then we also have done X-ray spectroscopy experiments, which is super sensitive to X-ray damage. And we saw no difference even when we are at the absorption edge of the manganese when we are below 15 femtoseconds. But we see huge differences when we go above. So the hypothesis currently is that we are on the kind of safe side when we are shorter than 15 femtosecond. But when we collect data at 40 femtosecond, then we have already X-ray damage involved. But you have to sacrifice it with most X-fields not being very well equipped to go to these shorter pulse durations. But we will have in October, when I told you we will do the time-reserved experiments with photosystem and X-ray spectroscopy, we will be hopefully able to go down to 5 femtosecond pulse duration. Because in the previous experiments we had, this is what will be totally safe side. So between 5 and 15, we should be able to see the fully undamaged structure. But still, even if you measure with 40, because of the fact that when crystals are not there anymore, they will just increase the background. You can measure really good data sets, and you outrun every secondary damage. We know where the radicals diffuse, and then like the crystal contacts, none of these effects happen. But when you really want to look at the electronic structure, like we want to do with the manganese cluster, then you have to go to faster pulse duration than the standard settings. And ideally, you want to go attosecond, where you would have no X-ray damage at all.
Okay, thank you. So 2 more questions came in from Armando Albert. First question is it realistic to think in structural solution from a single molecule? And the question says, okay, you can answer. Go ahead.
Yeah, maybe I answer that first. Okay, that's
yes.
Holy Grail. Okay, this is why they have actually built in the first place the X-fields. But we already simulated before the first X-fields operated in 2004 that the intensity is about a factor of 100 to 1,000 too low to get high resolution structures of a single molecule. So the X-field would have to increase by at least a factor of 100 or 1,000 to get to atomic resolution structures. And you think that is an impossible task, but I told you about the compact X-field seeding the big X-field. And so if we can build, either in Hamburg or in Arizona, these attosecond compact X-field fully lasing in all 3 dimensions, you could seed the big X-field with a small one. And this would then confer all the superior quality of the beam for the short from the mini X-field to the big X-field, and thereby then also be able to increase the intensity, because you would have all the intensity in this very narrow band of energy to the big X-field. So I think that is the way to go to get the X-field in the future up by another factor of 100 in intensity. And then you're in business for single molecule diffraction. And then you will be superior to cryo-EM, because you can do everything at room temperature. You don't have to freeze the sample, and you can directly get individual structures from diffraction from individual molecules in solution. So when you think about cryo-EM, a lot of people say, crystallography is dead, cryo-EM will completely take over. Cryo-EM was kind of in the sleeping beauty sleep for 25 years because they had this problem of X-ray damage. And only with this new direct detectors, they were able to solve it. Now, single molecule X-ray diffraction is behind cryo-EM when you look at single molecules, because the X-rays interact 1,000 times weaker with the matter than the electrons. But you have the advantage to do that at room temperature. So I think in 10 years, when hopefully the big X-field can be seeded by the small one, then we would be in business for single molecule diffraction at atomic resolution. And then that would be superior to cryo-EM. So therefore, we should not give up, but continue to work on that. And we think it needs a combination of a small X-field with a big one. And think about it, LCLS has cost 1.5 billion. The European X-field has cost more than 2 billion. And they need both of them about 200 to 300 million to run per year. So even if the compact one costs 50 million, when we build multiple of them, that would be practically, I would not say in the running budget, but it would be a minor upgrade to a big X-field to build a small one to seed it. So yes, we think that is possible, but not now.
Yeah, thank you.
15 years.
By the way, Armando said great. And the second question, also from Armando, how many unit cells are required to see diffraction?
That is a good question. So what we have seen with the photosystems, this huge large membrane protein, I told you that the smallest unit cell, also you can use the shape transform to get the shape, size and shape of the crystal. So in principle, we can tell you could tell you for the first 3 million diffraction patterns we got, for each of them, how big and the size and shape of the crystal was. The smallest one we saw was about 100 angstrom. And PS1 unit cell is 288 by 288 by 167. So we calculated that this would be just 3 by 3, or eventually even 2.5 by 2.5 by 7 unit cells. That was the smallest crystal we have seen diffraction from. Not at high resolution, but diffraction where we saw the shape transforms and could evaluate the data. So you can have really, really small crystals, but you would not get atomic resolution from these really mini ones at the moment, but when the intensity increases, that would also improve.
Okay, yeah. I don't see more questions in the chat, but oh, he said yes. Okay, there are 3 questions in the Q&A from Abel Moreno. He says, lovely and exciting talk, Petra, congrats. This is Abel Moreno from Mexico. Now on a sabbatical in Spain. Question, what is the most challenging molecules to be studied by X-ray?
The most challenging molecules to study by X-rays, that's a really good question. I think the most challenging molecules to study by X-rays are actually materials. So because the biomolecules have, thanks to bio-X-ray and us pioneering it, has actually made really great progress. But when you want to study materials, that is much more difficult because you have to bring them in, you have to shift the sample between the shots. It's not easy, you cannot just not jet these materials, and we just submitted today actually a proposal to propose X-ray studies on materials. So that's actually one of the things which DOE always complains about, that they said, you know, we built this big thing and now all the biologists do use the X-rays. So I think actually the most challenging things are actually studying materials with an X-ray. And because they will need a different type of sample injection. And we will also try to do that when we have the compact version ready soon. We will try applications both in the bio range and in the non-bio range. And then another really challenging thing is everything which can be expressed only in small amounts. So, because especially when you have a liquid jet and want to do mix and inject experiment, you need insane amount of protein because you run the jet with 50 meters per second. And so for a protein like a GPCR, that's completely off the limit. But with this idea of making these systems light-driven so that you can induce conformational changes in this much slower running lipid cubic phase, which runs instead of 10 microliter per minute with 0.1 microliter per minute, then we have a chance to do time resolved studies on essentially these proteins which don't express in large amounts, or you can isolate them from the natural source in large amounts. Now we have 150 liter bioreactor for making these photosystems, and we get only 5 milligrams out of this reactor. Also 150 liter cell culture and 5 milligrams of protein. So even the photosystems are not easy to make in half a gram amounts for these time resolved studies. So I think protein consumption is another really thing we have to work on reducing dramatically before you can use your very, very precious sample.
Okay, thank you, Petra. One more question from Juan Hermoso. He says, excellent talk, Petra. Do you expect to have large distribution of these compact X-rays worldwide? How about its cost? Is this affordable?
Okay, that's a good question. So we first were optimistic and thought that we could build the non-lasing version, which we are currently building, which is 300 femtosecond, but still really fast, for about 10 million. Well, it's more like 20 million. We were actually, we got from ASU 7, then they gave us another 3, but then we realized we need another 3, another 10, but then came the rescue with Leo Boyce and his wife Annette Boyce, which gave us a 10 million donation for completing the CXLS. So the CXLS, when we have finished it end of this year, will have cost, including all the personnel, also all the people building it, designing it, 20 million. But we think that we could build essentially that version very likely for about 12 million when we build it again, because the first prototype costs always most because you have all the people developing it and so on. And then the lasing version, as I said, he submitted an $80 million grant for building it, but from this 80 million, only like 18 million is materials, and the rest is all the people kind of working on it, developing it, building it, and so on. So the building cost itself might be about 15 to 20 million of a compact X-ray. And then you have to take the people into account building it. But when you build the third, fourth, fifth version of it, then the building will cost much less, because you have practically all the design which you need is already practically done. And we can also custom make them. So that means we can make one for more bio applications, one for material applications, and so on, because we are developing now this in parallel. It's a compact X-ray. So I think that the final price tag of a compact X-ray would be about 20 million.
Okay, thank you, Petra. Two more questions came in the chat. One from Jose Antonio Gavira. He says, thank you very much, great talk. Regarding sample delivery, which systems would you prefer? Jet delivery, rolling film, etc., and why?
So, for really fast time resolved studies, including the European X-ray, where the pulses come with only 1 microsecond spacing, the only suitable media is a liquid jet. But this is good also for mix and inject, but this uses insane amount of proteins. Like we made 0.5 gram of photosystem 1 and grow more than 10, I think more than 1,000 liters of protein for being able to do that. Okay, so then, so that is good for the super high fast repetition X-rays, but it's not good for sample consumption. Then the LCP is really nice because you can both grow crystals in the lipid cubic phase, but you can also deliver them in the lipid cubic phase, and this has much less sample consumption, but you have more background, so you cannot use the really nano crystals because you have a 50 micron jet instead of a 1 micron jet, so you have more background, and you cannot do the mix and eject experiment. So therefore we are trying to make it make the systems light driven. But when you just want to get a structure of a very difficult to crystallize protein, then I think the viscous injector is the best. And we have tested just as this beam time we had last week 4 different media, and we got our demo protein running in all of them. So we can inject, we can mix the crystals with agarose, PAC 8000, which was actually the best, grease, or different LCPs. So, and we have also very new, we have developed a cooling system, because the disadvantage of all the methods are so far that you can only deliver at room temperature. So when you have any crystal which you need grown at 4 degrees or 10 degrees, then this would be impossible. And we have installed a cooling system developed by Gerrit and Matthias Frank, and used it successfully at this beam time, where we could then, with a Peltier element, cool it. We get the water as a heat off from the other side by water. We installed all of this in just 30 centimeter by 30 centimeter helium chamber. And we are able to collect our data at 15 Celsius, which is where our crystals go. So this would be when you have temperature sensitive samples in small amounts and embedded in a viscous media and deliver them with the LCP jet. And then concerning sample consumption and hit rate, the best is actually fixed targets. We have just beam time in November at the PAL X-ray, where they had a simple chamber, more or less as a film. Then there's a grid, you put the crystals on, another film, captain film on top, you sandwich it, clamp it more or less, and then you collect data, not in individual chambers which you have hit, but in principle in this setup. We even did time-resolved experiments with that, with light flash coming in. And my team, which was there, Raimo, Jehao, and Katie, they said they assembled each chamber in 15 minutes, and this was what it took for measuring them. It took only 10 minutes to replace it. And the complete team was came back from the PAL X-ray, said, this is my favorite sample delivery method now, because you just apply the crystals, no clogging involved. You can even use bigger ones if you want. You sandwich it, and they got hit rates of up to 60, 70%. So that was awesome. So when you have enough sample and when you want to get the most data out of your beam, you should use fixed targets. But fixed targets is not as established as the jets yet.
Okay, thank you, Petra. Last question from Xavi. How much room is there for serial crystallography at synchrotrons?
Yeah, oh, this is really good. I have had not enough time. So actually, Jose is pioneering that. So the best person to ask is actually him. So he has done successful experiments at APS. And I think also now you start some at Alba, where you use the same jetting methods. And I think you can also use the fixed target methods to practically collect data at synchrotrons. So, the point is you need bigger crystals because the beam is less intense. And you have longer pulse durations, naturally, even if you use the single pulses of the synchrotron, in about, let's say, in the microsecond range. So you don't outrun the secondary damage. But because you measure serially, that means you shoot each crystal only once. For most proteins which don't contain metals, because metals will be a problem, because they will be then become reduced and could make conformation changes. But for normal proteins which don't contain metals, I think serial millisecond crystallography or microsecond crystallography at synchrotrons is a really valuable option because you have much more beam time. You can at this, and especially for this fixed target and the viscous media are the best, I think, for serial crystallography at synchrotrons because you don't need this insane amount of protein. So there is a lot of way for most proteins, and they're not just like photosystem 2 and then all these methods that you want to look at. Serial crystallography at synchrotrons is actually a spin-off from the SFX and might actually, maybe in 5 years, you have more structures solved with serial crystallography at the synchrotron and an X-ray, just because you have so much more access and you have more time also to develop new things than when you have only this one short period of beam time and one of the big X-rays. Ideally would be you combine then a synchrotron with a compact X-ray, and then you have best of both worlds. That would be really great.
Okay, Petra, thank you so much. No more questions. So I think it's also, we are nearly 20 minutes over. So which is, I mean, you forgot a lot of questions, which is great. We want to, I think we can finish the seminar. We want to thank Petra again for his fantastic talk on X-rays. Thank you very much, Petra. And thank you all for joining us.
Yeah, thank you very much. I would have loved to come in person, and maybe we can do that in 1 or 2 years when COVID is over.
Hopefully.
And then I can show you the first results already from our first compact machine, or from Axis in Hamburg, or both. Thank you so much.
Thank you, Petra.
Thank you, Petra.
Thank you all.
Bye-bye.
Bye-bye.